Okay. Find the cosine of the angle between these two planes. So we've got two planes, and you can imagine that the planes, if they intersect, are going to intersect with a certain angle of intersection. And that's the question here. How do you find that angle of intersection? The easiest way to do this is to look at the normal vector for one plane and the normal vector for the other plane. And it turns out that the angle between those normal vectors is going to be the angle between the planes. And you know how to find the angle between two vectors. What do you use in that situation? Yeah, so you'd use the dot product cosine identity to get the cosine of that angle, and then you'd use arc cosine to get at the theta. You may have noticed I sent around an email regarding this particular problem. I think it was this problem. Because a student had done what apparently was the correct work and punched it in and got the wrong answer. And what I did, I looked at the problem and looked at the answer, and I realized that although they don't say it here, they are interested in when two planes intersect, you can see that one of the angles is acute and the other one is obtuse. And it turns out that the angle that they want between the planes is the acute one. They don't say that, but that's what they want. So when you're doing the dot product, right, you don't really know whether you're going to get the acute one or the obtuse one, because you're getting the angle between the two vectors, right? And that angle could be obtuse, it could be acute, right? Okay. So if your two vectors are like this, then the angle between the planes is going to be precisely the angle between the two vectors that's given by the cosine identity. But if your vectors are like this, the angle given by the cosine identity is this obtuse angle. How do you get the acute angle? Take this from 180, right? Take this from pi. Okay.
Would, if you took if you had two vectors and you did the negative vector, would you get the acute angle too?
Exactly. So that's kind of what's going on, right? You don't really know because you haven't plotted these vectors which one you have, and so you don't really know until you get to the end. But that's exactly right. If let's say you did the problem and you got an obtuse angle, you could just stop there if you wanted. Instead of subtracting from 180, you could flip that vector over and do the problem again like this, and you would get the acute angle. So that's absolutely right. Again, it's not clear that they wanted the acute angle, but they do. Other questions?
Yeah, I just had a question on one of the exercises, number 10. It's not a web work one.
Sure.
It's where there's, like, it says there's a, it's like A1C. Yeah.
Yeah.
And I thought we could just like take, find the line between the 2 points that it gives us, and then use a unit vector, but it just like isn't coming out.
I like the idea of finding the line. Find the line between the 2 points. Once you find the line between the 2 points, ideas.
Well, you can make the equation for the line like initial point plus t times
The direction, no question.
And then you solve it so that they give you the middle coordinate has to be 1.
Exactly.
So it can be 1 plus.
So you find the t value. Find the t value that makes the middle guy 1. Then what?
Then you use that same value of t to get the other coordinates.
And then the other 2 coordinates are determined. Does that make sense? So find the t value that makes the... So first you find the equation of the line between these 2 points. Hopefully that's something that you can do. Once you get that equation, you've got these 3 coordinates. Find the value of t that makes that middle coordinate 1. And then whatever the other 2 numbers are, that's A and C. Other questions? Go ahead.
I was just curious about number 6, because so I wasn't really exactly sure how to go about it, and I was trying to find the equation for the line that it produces, for the intersection produces, but I guess I was overthinking it because I looked at the answer and realized that it was the plane that as a system of equations and just solve for the, I don't know, I just really didn't know how it worked out.
Okay. Find an equation of the plane containing the line of intersection of yada, 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 and perpendicular to the xy plane. Okay. What we need, what do we need to define the equation of a plane? What information do we need? Be more specific.
The vector perpendicular to the plane.
Right?
And then up one and down.
Okay, good. Ideas? How do I get that information from what I have?
It says that it's parallel to the xy plane, so that kind of gives you perpendicular.
Perpendicular?
Perpendicular.
Yeah.
I started by finding the equation of the xy plane and taking its normal vector, because if the plane is perpendicular to that plane, then the vectors are also perpendicular.
Not quite, but you're on the right track. Let me give you this hint. Can I find two vectors that are parallel to this plane that I seek? Can I find two vectors that are parallel to the plane that I seek? Why would that be useful? Let's just, everything else aside, why would it be useful to have two vectors that are parallel to the plane that I seek?
You can use those to find the.
I can cross them to get the normal vector. Can you find me two vectors that are parallel to the plane that I seek? You don't have to give them to me, but can you describe how I might find two vectors? If I'm perpendicular to the xy plane, I'm parallel to actually, no, right? Here's the xy plane, and I'm perpendicular to it. So I'm one of these guys, right? I'd be parallel to the z-axis. So there's a vector that's parallel to the plane that I seek, right? Pick one. Thank you. 0, 0, 1. So we'll stick with that one, tuck it away. We've got one line that's parallel. Okay. Sorry, we've got one direction that's parallel. A little bit subtler. The plane contains the line of intersection of these two planes. The plane contains the line of intersection of these two planes. What can you say about the direction of the line of intersection of those two planes?
It's also parallel.
It's also parallel. Right? If the plane contains the line, then the direction of the line is parallel to, so here we go. We've got this guy, and the z-axis is parallel to it. And then it also happens to contain the line of intersection of these other two planes. That's also a parallel direction. So here's a parallel direction, and here's a parallel direction. Once I get those two parallel directions, I cross product, and I've got a normal vector. And that's going to tell me how this thing is oriented. Okay. How do I find the direction of the line of intersection of those two guys? Sorry? Cross product of the normal vectors is going to be the direction of that line of intersection. Okay, so I've thrown a lot of stuff at you. Play around with it. See if you can make it, see if you can turn it into something. Oh, and you also need a point on the plane, right? How are you going to do that?
Can you take the coefficient? Just take 1
So this plane contains the line of intersection. So how are you going to find a point on this plane? Sure, find a point on the line of intersection. Is that hard or easy? It's not too bad, right? You just want to solve the 2 equations and the 3 unknowns, which you've done before. In fact, there are an infinite number of solutions. Just find one of them and that'll work. And yeah, you might even be able to eyeball it. Okay, can you find an x, y, and z that satisfy both of those equations simultaneously? I think I heard 0, 0, 1. All right. That's a good problem because it requires you to pull together a lot of different facts. Other questions? Yeah?
You sent a couple emails, but what work number 3?
Oh, good gravy. I don't have my keyboard with me either. Probably just killed my recording too. Okay. I suspect that that's from recording the desktop. Number which one?
Number
3. Oh yeah. Okay. So you're given a particular line and you're asked to compare it to these 4 other lines. And the way that you're going to compare them is you want to figure out if the first line is parallel, perpendicular, or neither to the second line. Okay, so here's 2 lines. They're parallel. Here's a line perpendicular, and here's a line that's neither. So you see how all 3 possibilities exist. Associated with every line, and part of the discussion in section 5, associated with every line is a direction. And what you're really being asked to do here is compare the directions of these lines. Are the directions parallel? Are the directions perpendicular? Or are they neither? We have tests at our disposal that let us tell whether 2 vectors are parallel, perpendicular, or neither, right? What's a test for perpendicularness? Describe it for me.
Just dot product the 2 together, and if you get 0, they're perpendicular.
Right. And how about parallel? Same. Or anybody? Parallel? Andy? If the cross product is 0, and by 0 we secretly mean 0, 0, 0, right? So if the cross product gives the 0 vector, then they were parallel. If the dot product gives a 0 scalar, then they were perpendicular. If neither of those things happens, then the 2 directions are neither perpendicular nor parallel. So you have this very straightforward way of testing the orientation, the relative orientations of 2 vectors. The real trick, I think, is how do you figure out what the directions are of these vectors? Let's talk a little bit about that. And I'll focus on the first one here, -t, 1 minus 4t. Okay, so here's the originally presented vector, and what I want to do, and this is a useful skill to develop, I want you to break that up into a constant piece and the t piece. And you'll notice also I've tacked on an extra 0 here. That's really out of convenience. It turns out that you can't do cross product really on 2-dimensional vectors, and you can do it fine on 3-dimensional vectors. And so this problem is talking about 2-dimensional lines in the xy plane, for example. It's perfectly fine to tack on an extra 0 to this vector, and then all you're really doing is taking the xy plane and embedding it in 3 dimensions. So now this line is not just living in 2 dimensions, it's actually living in the xy plane of 3 dimensions. But that's really the extent of it. It just changes your perspective a little bit, but has no effect on the math. So it's perfectly fine to tack on an extra 0 in a 2-dimensional problem like this. Okay. Does everybody see how I broke this up? I took the constant piece of this coordinate and put it here. Oh, which I think I screwed up. Excuse me. No, I didn't. I'm good. I did screw it up, though. Sorry. It's a skill I should develop. Okay. So there was no constant part here, so I get a 0. There was a constant part here, so I carried it through. And then there's no constant part on z. So I just put 0 there. The coefficient on t was -1 here. The coefficient on t was -4. And then in the third coordinate, I get 0. And how does this work? Well, this t is really just scalar multiplying this vector. And so if I want to undo this whole thing, I can just distribute the t onto each of the coordinates. And then if I really want to undo it, I can just add the 2 vectors together, and I'm going to go back to here. So does everybody see how to break that up algebraically? Why is it useful to break it up this way?
Gives you the direction.
Exactly. That's the direction of L. So now that you know how to pick off the directions and you have these quite lovely tests for perpendicularness and parallelness, I think you can do the problem, Henry.
If you do it without the cross product, just with seeing whether the direction vector of the one that you're matching
Is a multiple of the other one? Absolutely. So if you can look at the 2 vectors and you can see that one is a scalar multiple of the other, you don't need to do the cross product. Is that clear to everybody? But if you just want to sort of plug along and use these tests, cross product's fine. It's more work than is necessary because it's often quite easy to see that one is a multiple of the other. If one is a multiple of the other, then they're parallel. Other questions? Okay, we have a pretty modest goal today. I'm going to talk about section 6 today, which introduces 2 coordinate systems that are pretty useful in Calc 3 and in fact useful in physics, useful in engineering applications as well. And chemistry and some other hard sciences. I'm going to talk about the cylindrical coordinate system and the spherical coordinate system today for describing and locating points in 3 dimensions. How many of you guys have used other coordinate systems or know what I'm talking about when I say other coordinate system? It's okay to be like this, yeah. So what's another coordinate system that maybe you've heard of?
Polar.
And, okay, polar. So in what context would you guys have learned about polar? Or what context did you learn about it? Okay, so just straight up math class? Okay.
Yeah.
Okay, so polar coordinates, how many of you have heard of polar coordinates? Oh good, that'll help. So polar coordinates, let's talk briefly about them, and we'll use that as a segue. So the traditional coordinate system, which by the way has a name, it's the Cartesian coordinate system. Also called the rectangular coordinate system. And that's the traditional coordinate system that we use. And so we know that if we plot a point, it's going to go out a certain distance a along the x and up a certain distance b along the y. And we have this nice notation, a comma b, that indicates the coordinates and the location of the point. And so the polar coordinate system, you may remember, chooses different numbers to describe the location of the point. The numbers that they choose are r and theta. So r is the distance from the origin. Theta is the angle around the origin. So, for example, if I ask you where is 1 pi over 4, and we assume that that's polar coordinates, where are you going to put me? Yeah, in Cartesian coordinates, what would it be?
Root 2 over 2 up.
Root 2 over 2 up and root 2 over 2
Root 2 over 2
over, right? So I'm kind of at pi over 4 on the unit circle. Yeah, okay, good. And if I change the 1 to something like 3, what effect does that have? Yeah, it pushes you further out, but you're still an angle pi over 4 up from the x-axis. Okay, so yeah, that's good. That's very close to the cylindrical coordinate system that I'm about to discuss. Before I go there, let me ask you one more question. Describe the set of points that satisfy this equation in polar coordinates. What does it look like? Yeah. A line, okay. Be more specific.
It's continuous. At the end of it has to see.
I don't think you want to use the word continuous. It is a line. What's its direction? Or its slope? Yeah, it's 1, right? And what's its y-intercept? 0. So yeah, you could sketch this guy. Theta equals pi over 4. That's the line, theta equals pi over 4. How would you express this guy in Cartesian coordinates, this line? Y equals x, yeah. So we're going to start doing that. We're going to start talking about sets of points, like lines and planes, spheres, and cylinders, and so forth, in different coordinate systems. And you're already familiar with this. You're already doing this in Cartesian coordinates. And we want to start getting comfortable with thinking along these lines in other coordinate systems. Okay, so that's a bit of an intro. Let's talk about cylindrical coordinates. All right, cylindrical coordinates, it's sort of like you take the polar coordinate system and you add another dimension to it. It's really nothing more than that. It's not a super thought-provoking coordinate system. If you understand polar coordinates, you just tack on a z. Okay, not super elegant either, but you know, it has its purpose. Okay, so let me see if I can draw a picture for you. I'm going to look at just the positive. I'm going to pick a point out here in space, and to understand how to locate it in polar coordinates, what you have to do is you have to project down into the XY plane. And this guy here, this distance above the XY plane is the Z coordinate, so no change there. Theta is here, and R is this distance here. I hope that's not too hard to sort of visualize. Okay, let's talk about how to go back and forth between R theta and Z and X, Y, and Z. And
Just kind of back on the polar coordinates really briefly. If you're using those a lot, would you want to use like a grid that shows like distances from the center instead of X and Y?
yeah, if you do a Google search and do like polar graph paper, you'll find exactly what you're talking about. So polar graph paper does exist, but we're just so used to working in Cartesian coordinates that every thing I do in this class starts off with these coordinate systems. So we're always going to try to embed our coordinate systems in this more familiar context. But you're right. What I'd like to do is can I express X, Y, and Z in terms of R, theta, and Z? Well, certainly expressing Z is not going to be all that difficult. But R and theta, or X and Y, are a little bit more involved. And let me just try to sketch in a little bit of what I'm talking about. So if I have a particular point, in polar coordinates, can I find these red values, the X, Y, and Z? Okay, well that X distance is just this distance right here. The Y distance is just this distance, and the Z distance is here. So if you use a little bit of trigonometry, you should be able to figure this out, right? Okay. So let's use a little bit of trig, and let's talk about what X is equal to in terms of R and theta. R cosine theta, right? And Y is R sine theta, and Z is just plain old Z. And the other direction is equally interesting. If I know X, Y, and Z, can you tell me what R is? This is not, I don't think, written explicitly in the book, but it's a useful thing to have. So if I know X, Y, and Z, can I find R, theta, and Z?
Do the inverse tan, y.
Let's find R first. So can you find me R? Pythagorean theorem, yep. Square root of x squared plus y squared. And theta, I think you were onto it.
Oh yeah, inverse
Arctan
tan.
of y over x. Yep. And z is z. a lot of times you can figure this out just by, especially in the exercises in our book, you can figure it out just by sort of drawing and sketching a few triangles. But if you're really in a jam, you can pull out these formulas. Okay, so that's the cylindrical coordinate system. Any idea why that might be called the cylindrical coordinate system?
The volume of the cylinders, the area of the base times the height.
That's true.
So the area, to kind of show you what we used to pay attention to, the 2D surface, and then Z, and then our echo base.
So if you take, so I think the idea here is you start with circles in the XY plane and you tack on Z. And what happens if you take a circle in the XY plane and you sort of just let it sweep up and down and you sweep out a cylinder? So I think that's the idea. Okay. Let's talk about spherical coordinates. I'm going to go back to black. So spherical coordinates, again, are just another way of describing a location in three-dimensional space. And rather than use r, theta, and z, where r is the distance from the projection of the point into the xy plane to the origin, and theta is the angle of that projection around the origin, and z is the height above or below the xy plane, we choose different descriptions. Let me show you what those are. So in spherical coordinates, let me start again with our tried and true Cartesian coordinate system. By the way, I mean, the way that I'm visualizing this set of axes is y is going into the board, and that's the positive direction into the board. The reason for that is I'm trying to be consistent with a right-hand coordinate system where x cross y gives me z. So if I do x, if I point my fingers in the x direction and my palm towards the y direction, I get the positive z direction. So that's a right-handed coordinate system. So y, the positive y direction is into the board here. Okay, let's give ourselves another generic point. It's still useful to drop down into the xy plane and to sketch in some of these distances, some of these important distances. But the big picture here, let me get the way that we're going to define our coordinates in the spherical coordinate system is first the angle between the red vector and the z-axis in radians we will call phi. The angle between the projection of that red vector into the xy plane and the x-axis we will call theta. And the distance or the length of that red vector we will call rho, the Greek letter rho. Admittedly, it's difficult to figure out what's going on in this picture, but I hope hopefully along with the description, rho is the distance from the origin, phi is the angle from the positive z-axis, and theta is the angle between the projection onto xy plane and the x-axis. That's a little bit wordier, but hopefully you can kind of visualize it. This is similar but not quite the same as the coordinates we use to describe position on the Earth. Right? On the Earth we use latitude and longitude, right? In this coordinate system, when phi is equal to 0, where am I? I'm somewhere on the z-axis, right? When phi is equal to 0, does everybody see that? On the Earth, when I'm at latitude 0, where am I? I'm at the equator. And so there's this difference between latitude and longitude on the planet Earth and spherical coordinates. I'm not really sure why mathematicians and navigators decided to diverge on this particular issue, but they did, and it's an endless source of confusion. Okay. Theta, while we're talking about the Earth, theta equals 0. So theta corresponds to longitude, right? So latitude is how far north or south you are on the Earth, right? Positive latitude is above the equator, negative latitude is below the equator, or often we'll say 45 degrees north, 45 degrees south. Okay, you've heard that before? Okay. Longitude is sort of the vertical direction on the globe. Does anybody know where 0 longitude is? It's in the UK. It's in specifically, it travels through Greenwich in the UK. Why is that 0? Because when the world settled on this coordinate system, England was the top of the heap, right? You've heard of the good old British Empire, right? Spanned the globe. They were sending ships everywhere. When you're on top, I guess you get to make the rules. So the British set 0 longitude to be Greenwich, and it's stuck. Where's pi? 180 degrees. It's all the way around the other side of the world. It's the other. It's, you know, it sort of runs between. Does anybody know where it runs roughly? Yeah, it's through the middle of the Pacific Ocean. I think it actually shoots right through the Bering Strait, but I'm not sure. Between Siberia and Alaska.
I don't think it's a straight line.
Oh, well, it's a straight line in the abstract.
Yeah.
But I think what you're thinking of is the international date line. Yeah, which is sort of a ragged thing depending on political boundaries as much as anything else. So, yeah, I'm just trying to sort of get you an idea. Now, what's rho on the Earth? Distance from the center of the Earth to the surface. It's okay if you don't have that on the tip of your tongue. Might be like 6,000 miles or kilometers. Yeah, I have no idea. Those are two very different distances. But yeah, so on the Earth, rho is a constant. If you're on the surface of the Earth, rho is a constant. But these other two things, latitude and longitude, vary, and they can describe your position on the Earth. And I use the word rho constant loosely, right? Your rho is very different if you're at the top of Mount Everest than if you're in Death Valley. But relative to the entire Earth, not so much, right? If you think about the Earth, let's say it's 4,000 miles or 6,000 miles or whatever, and then you go up a puny 5 miles to the top of Mount Everest, you know, not very significant. So effectively speaking, when you're wandering around on the surface of the Earth, your rho is constant. Okay, what's our phi here in Washington State? Does anybody know? Do you know what our latitude is here in Washington State? Ish. Not quite, a little higher. The Washington-Oregon border actually is actually on the 45th, which is interesting, right? What's special about 45? Halfway from the equator to the North Pole. So our latitude is almost exactly halfway between the equator and the North Pole. Just interesting fact. What's our phi? pi over 4. Who has a bigger fee, Washington State or Louisiana?
Washington State.
Louisiana, yeah, right? It's because it's backwards. Who has a bigger latitude in degrees, like on latitude, longitude degrees? Washington. Who has a bigger fee? This is backwards. It's really annoying. Okay. Let's talk about a few of these. Go ahead.
Is phi 0, does that mean it's on straight up and down, or it's flat? Like, is phi 0 the z-axis, or is it the xy plane?
Phi 0 is the z-axis.
Okay.
Yep. What's theta 0? X-axis. What's rho 0? The origin. The y-axis feels left out. Can we get the y-axis in there? Theta would be pi over 2, right? What would phi be? I should have been more careful with the x-axis too. I'll go back to that. To describe the y-axis, theta is pi over 2. What's phi? Pi over 2 also. I've got to have both of those to be on the y-axis. And then rho can be anything. X-axis. Phi has to be pi over 2 to get me down into the xy plane. And then theta is 0, right? And then rho can be... There's a little bit of debate about whether you should allow rho to ever be negative, or in cylindrical coordinates, whether you should ever allow r to be negative. We'll be okay with that. We'll just say, yeah, as long as we know what we're talking about. What do we mean when rho is negative? Because here I defined it as distance from the origin, right? Distance can't be negative.
Is it like you do everything normal, acting like it's positive, and then just flip it?
Exactly. Okay, so just treat rho as if it's positive, and then go back 180 degrees the other way. Okay. In practice, when you use spherical, cylindrical coordinates, in practice, these values are positive because they represent distances. And when you're in the physics class and when you're in engineering class or what have you, it's safe to think about these things as being positive. Some math problems will throw negative rhos at you and negative r's at you, and what that means is just flip it around 180 degrees. So just be on guard for that.
So instead of using negative rhos, do they just describe it as really large ph's and thetas?
Exactly, right? I mean, and to me, I think that's the more appropriate way. If I were running the show, I would just say, no, rho is going to be non-negative. So, because you can always get to that other side just by tweaking theta or phi. Okay. You haven't, I guess, a more concise way of putting it is you haven't lost anything by restricting rho to be non-negative. You don't lose any space. Okay. Let's look at a few examples and then we'll call it a day. I just want to talk about one. I don't want to actually do it. Convert the following points in rectangular coordinates to cylindrical and spherical coordinates. So here, you plot 1, 1, 1 in rectangular coordinates, and then you try to suss out what are the cylindrical coordinates. Let's see if we can do this just thinking about it without sketching too much. 1, 1, 1. Let's do cylindrical. What's r? Root 2. Right? Think about the xy plane. You go over 1 unit, you go up 1 unit. Right? What's that diagonal? That's r. Pythagorean theorem says that's the square root of 2. In that same picture, in that same context, what's theta? 45 degrees pi over 4, right? So now you've got r and theta. What's z? 1. That's easy. Okay, so that's kind of the process that you have to go through, and I'm not sure how useful it is to try to sketch this stuff out more than just kind of visualize it in your head. Because I'm not sure that I could draw it in any way that would be useful to me solving the problem. I certainly probably couldn't draw it in any way that would be useful for you guys solving the problem. So,
What's the y coordinate?
well, x, y, and z are all 1, 1, 1.
So it's all root 2.
So r is root 2, theta is pi over 4, and z is 1. What about b, I guess, while we're talking about this? Let's do cylindrical. So r is determined by those 2 7s, right? What's that, like root 98 or something? Whatever that is. Angle? Yeah, and I think it's really worth thinking about, okay, you're out 7, and then you're out 7, and then you're down 7, so you're down here. What's that angle? You can call it either negative pi over 4, or you can go all the way around and call it 7 pi over 4. Either one is fine. Okay, you do have that ambiguity with these coordinate systems that use angles, because you can wrap around as much as you want. So in fact, you could add multiples of 2 pi and still get the same coordinates. Okay, let's keep going here.
Wait, so if we're going to do that in spherical coordinates,
Mm-hmm.
how would we find phi?
Okay, let's think about it for a second. So want to do B or A? Let's do A just because it might be a little bit easier to think about. So in A, what's rho? Square root of 3? Square root of x squared plus y squared plus z squared. It's the distance from the origin. Okay. Let's think about this some more. How are we going to get our hands on phi? So we've got that root 3 that's rho. If we could just get our hands on one more distance, we might be able to get that angle down here. I will sketch that for you. I think it's worth. Okay, so I've got this distance root 3 and I've got this angle phi. Do I have enough information to get my hands on phi?
If you make a right triangle with one side on the x-axis and you know how tall it is, it's just going to be 1 tall.
Right, z was 1 in this case. God, what happened there? Okay, so now we know 2 distances. Is that enough to get phi? Because as you note, this is a right triangle.
Yeah, you can do, like,
What's the right ratio? So you know the adjacent side and you know the hypotenuse. And to get phi, whatever that is, I don't know if that's a nice one or not, is it? It's not really coming to me as being a good one. By nice, meaning one that you could pick off from the unit circle. Okay, so you just kind of have to suss it out. Build right triangles, identify lengths, and suss it out. The other direction's usually pretty easy. If you know the spherical coordinates, it's easy to get the x, y, and z coordinates, right? Because we have these explicit formulas. Actually, I haven't done those explicit formulas, but they're in the book. I'll let you read about them. Again, it's more trigonometry. I'll show them to you, though. So it looks worse than it is. If you just follow the trigonometric explanation here, you'll see why x, y, and z are those values. Here's a fun thing. What's the equation of a sphere in Cartesian coordinates centered at the origin and radius 2. What does that look like? X squared plus y squared plus z squared equals 4, right? What does that equation look like in spherical coordinates? In other words, what does it look like if I use the variables rho, theta, and phi? Well, it's actually not that hard to figure out because all you have to do is use this substitution. Everywhere you see an x, use rho sine phi cosine theta. Everywhere you see a y, everywhere you see a z, make those substitutions. Let's do that. It's pretty cool. Square everything, and you see there's a common factor of rho squared. And what's left behind is sine squared phi cosine squared theta sine squared phi sine squared theta cosine squared phi. And this has a really nice simplification. So it looks like a mess, but it's actually not. If you stare really closely at the first two terms, there's a common factor of what? Sine squared phi. If you factor that out, what's left behind? Cosine squared theta plus sine squared theta, which is 1. So the first two terms really collapse into sine squared phi. And that collapses into 1, and you get rho squared is equal to 4. Rho equals 2. So in spherical coordinates, the equation of a sphere is quite simple. And that's almost by design. It's kind of the point of spherical coordinates. Other shapes have less clean representations. For example, and I think one of the exercises in the book talks about a plane. Let me see if I can find it here. Number 3, find an equation for the YZ plane in cylindrical coordinates. Find an equation for the YZ plane in cylindrical coordinates. What's the equation of the YZ plane in Cartesian coordinates? X equals 0, very good. It's very simple. Right? But yes, that is the equation of a plane. For example, what's the normal vector if you stare at that thing? 1, 0, 0. You pick off the coefficients of x, y, and z. The coefficient on x is 1, the coefficient on y is 0, and z is 0. So yeah, that's the equation of a plane. Strange but true. Okay. Suppose I want this in cylindrical coordinates. What do I do?
Plug in, so x equals r cosine theta.
Yeah, that's the equation of the YZ plane in cylindrical coordinates. However, we can actually simplify this a bit. Don't have to worry so much about r, right? Because r, it might be 0, but you know, it's mostly not 0. That's kind of what where I'm headed. Yeah. Okay, so let's talk a little bit about this. The YZ plane, let me think about it. Here's the x, here's the z, here's the y. So here's your yz plane. How do I get onto that plane? How do I get myself onto that plane using cylindrical coordinates? The angle pi over 2. So here's the x direction, right? I go an angle pi over 2, and I'm in the plane. Does it matter what my r is? Not so much. And how about my z? Not so much. So pretty much done. Cosine theta equals 0, theta equals pi over 2. So there's the equation of the yz plane in cylindrical coordinates. Time for maybe one more. Trying to find a good, interesting one here. How about 10? The equation of the cylinder x squared plus y squared equals 4 in spherical coordinates. First of all, they called that a cylinder. Why is that a cylinder? Yeah.
Because it's a circle on the XY plane and that has all these.
Right. So all I have to do is be in the circle of radius 2, center of the origin in the xy plane, and my z coordinate can be anything. So that gets me here and anywhere up and down. So that's why that's a cylinder. Good. How do I find an equation in spherical coordinates for the same shape? Substitute, right? Just do that substitution. So let's drop in rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals 4. Does everybody see what I did? There's a common factor of rho squared sine squared phi in both of the terms on the left-hand side. And I get that familiar sine squared theta, cosine squared theta identity. This collapses into that. And, you know, you could take the square root here, I suppose. In fact, yeah, let's do that. Why do I not have absolute values on sine phi? So here's the z-axis. Phi is the angle from the z-axis. What range of phis does it take to cover the whole space? I go from 0 out to pi, right? What's the sign of sine? The sign of sine on that range? It's positive. So I can just drop that. And rho sine phi equals 2 is the equation of the cylinder. Okay. So there are problems for you guys to tackle, and then Friday we'll do some review. We'll try to review the whole chapter 12, and then Monday we'll start probably start hitting the first bit of calculus. Okay. See ya.